and welcome back to my series of videos for General Chemistry 1. Today I want to tell you about one of the reasons that elements have the colors they have, and that'll lead us to find out how we can tell what stars and galaxies thousands of light years away are made of. It'll also let us talk about one of the most famous models we have for the structure of the atom. When atoms have a lot of energy, one of the most common ways for them to release that energy is in the form of light. It turns out that a given element only gives off light at specific wavelengths, and this is something you've probably noticed even if you don't usually think about it. For example, you may have noticed that the light given off by certain kinds of headlights have a distinctive blue color. That's because these headlights contain a small amount of mercury vapor. An electrical current is passed through the vapor, and the mercury gives off the blue light that you see. You may also have noticed that some old street lights give off a yellowish colored light. That's because of sodium vapor in the light bulb, which glows yellow when an electrical current is passed through it. It turns out that every element emits a different set of wavelengths. For example, here are the colors given off by several elements including mercury and sodium. You can see that there are prominent blue and purple lines for mercury, which is why the mercury headlight looks blue, and the sodium spectrum has lines in the yellow region. You can also see that neon has lots of red lines, which is why neon lights have a red color. The lights that are other than red in this picture must use elements other than neon, because the color given off by each element is always the same, so the neon is always going to be red. Spectra like this are called emission spectra, and one of the great mysteries of science in the early 20th century was, why do elements emit these exact wavelengths of light? We'll talk about that question and how exactly it was solved in the course Physical Chemistry, which I hope you'll take one day. But answering this question was the most famous and important contribution Niels Bohr made to chemistry. It's this research that Bohr was awarded the Nobel Prize for. You might remember that way back in video 3 of this series, we talked a little bit about Bohr's model of the atom. The important thing to remember is that in Bohr's model, the electrons orbit around the nucleus, and these orbits, sometimes also called shells, can be numbered 1, 2, 3, and so on. Bohr used this model to explain the emission spectrum for hydrogen. Here's how. It turns out that the energy of an electron depends on which orbit it's in. Here's a simple equation for that. It tells you that the energy is proportional to -1 over n squared, where the n is the number of the shell. There are a few things to notice about that equation. First is the negative sign. That's there because electrons have lower energy the closer they are to the nucleus. That makes sense. The nucleus has a positive charge, and the electron has a negative one, so they're attracted to each other. They want to be as close as possible, so when the electron is in the smallest shell, where n equals 1, it'll have the lowest energy. So let's make a diagram of the energies for these shells. I'll put the energy on the left side and n, the number of the shell, on the right side. We'll start with the first shell, where n equals 1. This formula tells us that the energy will be proportional to 1 over n squared. If we plug in 1 for n, that tells us E is proportional to -1. For the next shell, n equals 2, and that means the energy is proportional to -1/4. Next is n equals 3, which means that E will be proportional to -1/9. If we continue on, we get a diagram that looks like this. There's a lot of interesting information in this diagram. First, notice that the energies are closer and closer as we go up the chart. The second thing to notice is that as n gets higher and higher, the energies get closer and closer to 0. So, the energy is lower when the electron is close to the nucleus, and it gets higher as the electron gets further away. Eventually, when the electron is so far away that it isn't attracted to the nucleus anymore, the energy would be 0. So, how does this help us explain the emission spectrum of an element? Suppose we have an electron in the n equals 3 level, so that it has an energy over here. The electron wants to get closer to the nucleus, so if it can, it'll move to the n equals 1 level. But that level has a lower energy. So in order for it to go there, the electron will have to lose energy. It'll do that by giving off light. But think about what that means. When an electron goes from the n equals 3 to the n equals 1 level, it will always need to lose the same amount of energy. In the last video, we saw this equation, which tells us that the amount of energy a light wave has tells us the frequency of it, and that determines its color. So, whenever an electron goes from the n equals 3 to n equals 1 level, it always emits light of the same frequency, and therefore the same color. And what color will that be? It turns out that we can determine that using this equation. In this equation, NF and NI are the final and initial levels of our electron, and RH is a constant called the Rydberg constant. It has a value of 1.0968 times 10 to the 7th meters to the minus 1 power. That's a number I'll give you on tests and quizzes, so you don't need to memorize it. The answer that we get, though, will be 1 over lambda, which you might remember is the symbol for the wavelength. So let's see how this equation works. We were just talking about an electron moving from the n equals 3 to n equals 1 level, so we can use this equation to find out what color of light this would give off. The initial energy level is 3, so Ni will be 3, and Nf will be 1. Don't forget that we need to square both of those in the denominators. Next, we subtract the two fractions. 1 over 1 minus 1/9 gives us 0.88889. Now we multiply that by the Rydberg constant, and we get 9.7493 times 10 to the 6th meters to the minus 1. What we really want to know is the wavelength, so we'll need to take the reciprocal of both sides of this equation. That gives us lambda, the wavelength, on the left, and 1.0257 times 10 to the minus 7 meters on the right. What color is that? Well, if you check the electromagnetic spectrum, you can see that this is an ultraviolet wavelength. It's not something we could see with our eyes, but there are plenty of instruments that would be able to detect it. So, whenever an electron drops from one energy level to another, it emits a certain wavelength of light. And the wavelengths of light for every element will be different, and that makes it possible for us to determine what elements are present in stars and nebulas, even though they're hundreds or even thousands of light years away. One thing I should mention is that this equation is specific for hydrogen. If we want to determine the wavelengths that other elements give off, we have to change the equation just a bit. But that's something that we'll talk about in the physical chemistry course. That's enough new material for today, but when we meet again, we'll be ready to talk about one of the most strange and surprising discoveries made in the field of quantum mechanics. It's something that changes our whole picture of the entire physical universe around us. Hopefully it's something that will hurt your brain a little bit to think about, but in a good way. So until next time, have a good week.